Hello, and welcome to Somniora Mind. Tonight, we will journey to a place beyond imagination. Perhaps it has been a long day, and you're ready to leave everything behind for a while. Or maybe you're the kind of person who finds rest not in silence, but in being carried through something vast, something so immense that every worry quietly fades away. Either way, tonight is for you. We are about to travel across the universe, not only through our solar system, and not merely within a single galaxy, but across the entirety of existence itself, from the first moments of light ever born to the farthest reaches we can observe, and even beyond. Together, we will journey through the earliest moments after creation. We will pass through cosmic nurseries where stars begin their lives, venture into the depths of black holes, and drift across the vast and silent spaces that separate entire galaxies. Along the way, we will witness ancient and mysterious light, colossal structures, unexplained phenomena, and the fundamental building blocks that quietly hold everything together. And before we begin, if these peaceful journeys bring you comfort or help you relax, consider supporting the video with a like or subscribing to the channel. If you're someone who finds wonder in the hidden mysteries of existence and the universe, then this place was made for people like you. Those who enjoy losing themselves in the unknown. The vast universe awaits us. Tonight, before our journey comes to an end, you will encounter something so strange it seems to bend time itself, and something so beautiful that it has remained hidden in plain sight for 10,000 years. But there is no need to rush. We will move slowly, peacefully, connecting with one mind at a time. Now let us begin. The universe is approximately 13.8 billion years old. It is such a vast number that it challenges ordinary intuition, yet astronomers have measured it with remarkable precision by studying the oldest light in the cosmos, a faint glow known as the cosmic microwave background, which still fills all of space like the dying warmth of the universe's first fire. By mapping tiny variations in this glow, scientists have traced the cosmos back to its very beginning. Not exactly to the moment of the Big Bang itself, but to a fraction of a second afterward. 13.8 billion years is not just a number. It is the age of everything. The age of every star, every atom, every quantum of light that has ever traveled through this vast and silent place. The universe began incredibly hot and incredibly small. In its earliest moments, everything that exists today, every galaxy, every star, every grain of dust, every atom in every living being, was compressed into a space far smaller than the period at the end of this sentence. The temperature was so extreme that the four fundamental forces of nature, gravity, electromagnetism, and the nuclear forces, were unified into a single force. The concepts of space and time as separate things may not even have applied. Then expansion began. Not an explosion into empty space, but the expansion of space itself, carrying everything along with it. The universe did not appear inside something else. It was everything, expanding outward from its first breath. It was an intensely hot soup of quarks and gluons, the fundamental ingredients from which protons and neutrons would eventually emerge. This plasma existed for only a fraction of a second before cooling enough to allow quarks to bind together. In laboratories here on Earth, physicists have briefly recreated this state by colliding heavy atomic nuclei at nearly the speed of light. For a fleeting instant, matter becomes something older and simpler than anything that has existed in the universe for billions of years. It is a window into a time before atoms, before even their components, a glimpse into the earliest architecture of the universe. For the first 380,000 years, the universe was opaque. During this early period, The cosmos was so hot and dense that photons, particles of light, could not travel freely. They were constantly absorbed and re-emitted by the hot plasma, trapped in a thick fog of energy and matter. The universe was bright, but nothing could see across it. Then, as the cosmos expanded and cooled, electrons slowed down enough to be captured by atomic nuclei, forming the first neutral atoms. In that moment, the fog cleared. Photons streamed freely through space for the very first time. The light released in that clearing is the cosmic microwave background that astronomers still detect today, stretched by billions of years of expansion into radio waves, filling all of space with the afterglow of a universe learning to see. The first stars were enormous and nothing like the sun. Once matter had cooled and clumped together under gravity, the first generation of stars, known as population 3 stars, began to form roughly 100 to 200 million years after the Big Bang. These stars were unlike anything in the modern universe. They contained no metals, no carbon, no oxygen, no iron, only the hydrogen and helium forged in the earliest minutes. Without heavier elements to cool collapsing gas clouds, they grew far more massive than modern stars. Some may have been hundreds of times the mass of our Sun. They burned brilliantly for only a few million years before exploding as supernovae, scattering the first heavy elements into space and seeding future generations of stars, planets, and eventually, life. No population 3 star has ever been directly observed. They are too distant, too ancient, but their legacy is in everything. The universe went dark for hundreds of millions of years. Between the clearing of the early fog and the formation of the first stars, there was a period of cosmic darkness. No stars shone, no galaxies existed. Gravity quietly pulled matter together through the darkness, assembling the seeds of future structure in silence. This era, known as the Cosmic Dark Ages, stretched for perhaps 100 to 200 million years. It ended when the first stars ignited and sent ultraviolet light blazing outward, gradually reionizing the hydrogen gas that had been neutral since the fog cleared. This epoch of reionization represents the universe lighting itself up for the first time. A slow cosmic dawn spreading over tens of millions of years until the darkness was finally, gently, replaced by the first light of a star-filled universe. Everything visible in the universe makes up less than 5% of its total content. This is one of the most disorienting facts in all of science. Every star, every galaxy, every planet, every atom of gas and dust, every photon of light, all the things we can see or detect with instruments, account for roughly 4 to 5% of the total energy content of the universe. The remaining 95% consists of two things we cannot see and barely understand. About 27% is dark matter, which interacts with gravity but not with light, holding galaxies together and acting as the invisible scaffolding of cosmic structure. About 68% is dark energy, a still mysterious force causing the universe's expansion to accelerate. We live in a cosmos made almost entirely of things we do not yet understand. The universe is not just expanding, it is accelerating. For decades after the Big Bang Theory was established, astronomers assumed that the expansion of the universe must be slowing down, pulled back by gravity from all the matter within it. In 1998, two independent research teams studying distant supernovae discovered something that changed cosmology entirely. The expansion was not slowing down. It was speeding up. Something was pushing the universe apart, overcoming gravity on the largest scales. This force, dubbed dark energy, remains one of the deepest unsolved mysteries in physics. Its nature is unknown. It may be a property of space itself, or something more dynamic? What is certain is that it will shape the future of the universe more than anything else. A slow, relentless acceleration that will eventually carry distant galaxies beyond our observational horizon forever. The observable universe is about 93 billion light-years across. Since the universe is 13.8 billion years old, one might assume the farthest we can see is 13.8 billion light-years in any direction. But space itself has been expanding during those 13.8 billion years. The light that reaches us now from the edge of the observable universe was emitted when its source was much closer, but that source has since been carried far away by expansion. Taking this into account, the observable universe, the sphere of space whose light has had time to reach us, spans roughly 93 billion light-years in diameter. Beyond that horizon, the universe almost certainly continues. We simply cannot receive light from regions where expansion has carried matter faster than light could travel to us. There may be more universe than we will ever be able to see. The universe may be infinite. While the observable universe is finite, cosmologists have found no evidence that the universe as a whole has an edge or a boundary. The geometry of space on the largest scales appears flat, meaning it does not curve back on itself like the surface of a sphere. If the universe is truly flat and infinite in extent, then the observable region we can see is an infinitesimally tiny fraction of everything that exists. An infinite universe would imply infinite repetitions of any arrangement of matter, because in an infinite space, every possible configuration would occur not once, but endlessly, an idea both dizzying and strangely peaceful. We do not know whether the universe is infinite, but we have found no reason to believe it ends. In 2016, a more thorough analysis of data from the Hubble Space Telescope revised that estimate dramatically upward. There may be 2 trillion galaxies, 2 trillion, in the observable universe, most of them too small and faint for current telescopes to see directly. Each galaxy contains anywhere from millions to hundreds of billions of stars. The scale of the cosmos is not just large. It is so vast that our language and our minds have no adequate container for it. We are quieted by it in the way one is quieted by standing at the edge of an ocean at night. Stars are being born right now, in clouds of gas and dust drifting through galaxies. Star formation is not a historical event. It is happening continuously all over the universe at this very moment. Giant molecular clouds, composed mostly of hydrogen gas and traces of heavier elements, drift through the spiral arms of galaxies. When these clouds are compressed by the gravity of nearby stars, the shock wave from a supernova, or a chance collision with another cloud, regions within them begin to collapse. Gas falls inward under gravity, heats as it does so, and eventually reaches the temperatures and pressures needed for nuclear fusion. A new star ignites. Our own solar system was born this way 4.6 billion years ago from a collapsing cloud seeded with material from older, dying stars. The universe has been making new suns ever since its first few hundred million years, and it continues tonight. The sun converts 4 million tons of its own mass into energy every second. At the core of our star, temperatures exceed 15 million degrees Celsius, and pressures are so immense that hydrogen atoms are fused into helium through nuclear fusion. In each of these reactions, a tiny fraction of the mass involved is converted into pure energy according to Einstein's famous equation, E=mc². Every second of every day, the sun loses roughly 4.4 million tons, not in the form of material expelled into space, but as pure energy radiating outward in all directions. Some of that energy travels for 8 minutes across 150 million kilometers and arrives at Earth as sunlight. The warmth on your face on a sunny afternoon is the result of mass being annihilated 150 million kilometers away, one tiny fraction of a ton at a time. The sun is currently about halfway through its life. At about 4.6 billion years old, the sun has used roughly half its available hydrogen fuel. It will continue burning steadily as a main sequence star for another 5 billion years or so before its character changes. In that far future, the sun will swell into a red giant as it begins fusing helium in its outer layers, potentially expanding to engulf the inner planets. Eventually, it will shed its outer atmosphere as a beautiful planetary nebula and leave behind a white dwarf, a dense, slowly cooling remnant about the size of Earth. This fate is not unusual. It is the standard life cycle of a star like ours. Every atom of carbon, oxygen, and nitrogen in your body was forged in a star that went through some version of this same process. Stellar death is the prerequisite for planetary life. Supernovae are among the most energetic events in the universe. When a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel, its core collapses in a fraction of a second. The outer layers, falling inward at a quarter the speed of light, rebound off the dense collapsing core and are blasted outward in an explosion called a supernova. For a brief period, a supernova can outshine an entire galaxy containing hundreds of billions of stars. The energy released in this single event exceeds what the Sun will radiate in its entire 10 billion year lifetime. Supernovae are also the primary forge for heavy elements: iron, nickel, gold, uranium, which are scattered into space and eventually incorporated into new generations of stars and planets. The iron in your blood and the gold in every piece of jewelry ever made were created in the deaths of stars. Neutron stars are the densest objects with a surface in the universe. When a massive star's core collapses in a supernova, it may form a neutron star, an object roughly 20 kilometers across that contains more mass than the Sun. Neutron stars are so dense that a teaspoon of their material would weigh roughly 1 billion tons on Earth. Their surfaces are composed of a crystalline lattice of atomic nuclei and free electrons, and their interiors may contain forms of matter, such as quark matter, that do not exist anywhere else in the universe. Neutron stars rotate rapidly, some spinning hundreds of times per second. When they emit beams of radiation from their magnetic poles, we detect them as pulsars, cosmic lighthouses sweeping through space with extraordinary precision. Some pulsars keep time so accurately that they rival atomic clocks. Black holes are not holes at all, they are objects. The word hole suggests emptiness and absence, but a black hole is the opposite, the densest possible concentration of mass. When a massive enough stellar core collapses, gravity overcomes all other forces, including the pressure of neutrons against each other. Matter continues collapsing without limit, at least according to our current understanding, forming a singularity, a point where our equations break down. Surrounding this singularity is the event horizon, the boundary beyond which gravity is so strong that even light cannot escape. Anything that crosses the event horizon is gone from the observable universe forever. Black holes do not suck material in. They simply sit there, like any massive object, pulling on nearby matter through ordinary gravity. They are invisible against the darkness of space, detected only by their effects on the light and motion of things around them. Supermassive black holes lurk at the center of nearly every large galaxy. The center of our own Milky Way contains a black hole called Sagittarius A*, with a mass more than 4 million times that of the Sun. The center of the galaxy M87 contains a black hole about 6.5 billion solar masses, so large that our entire solar system would fit comfortably within its event horizon. These supermassive black holes are thought to have grown over billions of years through the accretion of gas and the merging of smaller black holes. How they first formed remains an open question. When actively feeding on infalling gas, they become quasars, blazing objects so bright they can be seen across most of the observable universe. Even in their dormant state, they exert an enormous influence on the evolution of their host galaxies, regulating star formation and shaping the large-scale structure of the cosmos. Light from the most distant objects we can see has traveled for over 13 billion years to reach us. When astronomers look at the farthest galaxies, they are not seeing them as they are now. They are seeing them as they were in the distant past. Light travels at approximately 300,000 kilometers per second, which means that every observation is a form of time travel. Looking 1 light year away means seeing 1 year into the past. Looking billions of light years away means seeing billions of years into the past. The most distant objects detected so far are galaxies that existed when the universe was only a few 100 million years old, less than 5% of its current age. In every direction we point our telescopes, we are looking backward through time, watching the universe gradually assemble itself from the chaos of its first moments. The speed of light is the ultimate cosmic speed limit. Nothing with mass can travel at or beyond the speed of light in a vacuum, approximately 299,792 kilometers per second. This is not a technological limitation. It is a fundamental property of the universe. As an object with mass accelerates toward the speed of light, the energy required to accelerate it further increases without bound. Reaching the speed of light itself would require infinite energy. Light achieves this speed because photons have no mass. Even within the context of general relativity, where space itself can expand faster than the speed of light, no signal or information can be transmitted faster than light through space. This limit shapes everything about how we perceive and interact with the cosmos. The distances between stars, the isolation of galaxies, the ultimate fate of an accelerating universe in which distant regions will forever recede beyond our reach. The universe has a large-scale structure that resembles a cosmic web. On the very largest scales, the universe is not uniform. Galaxies cluster together along vast filaments of matter, separated by enormous voids that are nearly empty. This network of filaments, walls, and voids, called the cosmic web, is the largest known structure in the universe, spanning billions of light years. The filaments are composed mostly of dark matter, with ordinary matter, galaxies, and gas, tracing the visible outline of the dark matter scaffolding beneath. The voids between filaments contain very little matter and very few galaxies. The pattern of the cosmic web emerged from tiny quantum fluctuations in the very early universe, magnified by billions of years of gravitational amplification into the grand architecture of matter we see today. The universe is not scattered randomly. It is organized, on the largest scales, into a structure of almost incomprehensible elegance. The largest known structure in the universe spans more than 10 billion light years. Called the Hercules Corona Borealis Great Wall, this vast assembly of galaxies and filaments stretches across more than a tenth of the observable universe. Its existence poses something of a puzzle. Given the age of the universe and the rate at which structure grows, cosmologists would not expect anything this large to have assembled in 13.8 billion years. Whether it truly constitutes a single coherent structure or is a statistical fluctuation in galaxy surveys is still being debated. But the fact that such concentrations of matter exist at all tells us that the early universe had fluctuations on scales we are still working to fully understand. The cosmos builds things on scales that dwarf every other concept of large we have ever imagined. Cosmic voids are the emptiest known regions of space. Between the galaxy filaments of the cosmic web lie vast regions called voids, where matter is exceptionally sparse. These voids can span hundreds of millions of light years. Inside them, galaxy counts drop to near zero. The largest known void, the Boötes void, spans roughly 330 million light years across and contains far fewer galaxies than cosmologists would expect. Traveling through the Boötes void at the speed of light would take 330 million years with almost nothing to see. Voids are not truly empty. They contain some isolated galaxies, diffuse gas, and dark matter. But they represent the quietest, most solitary regions of the universe. In the structure of the cosmic web, the filaments are where things happen. The voids are where the universe rests. Light bends around massive objects. Einstein's general theory of relativity predicts that mass warps the fabric of space-time, and light must follow the curves of that fabric. This means that when light from a distant object passes near a massive body, a galaxy cluster, for example, it is deflected just as a ball rolling across a curved surface is deflected from a straight path. Astronomers call this gravitational lensing, and it has become one of the most powerful tools in cosmology. In some cases, gravitational lensing produces multiple images of the same background object or stretches it into an arc or ring. In other cases, it magnifies distant objects, allowing us to see galaxies that would otherwise be too faint to detect. Every massive object in the universe acts as a natural lens, bending and reshaping the light of everything beyond it. The universe is permeated by a faint glow left over from the Big Bang. The cosmic microwave background, or CMB, is thermal radiation that fills all of space with exquisite uniformity. It was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and the opaque plasma cleared. Since then, that radiation has been stretched by the expansion of space from visible and infrared light to microwave wavelengths. Detected in every direction we look, the CMB is a snapshot of the universe at 380,000 years old, covering the sky like wallpaper printed in the earliest moments of cosmic history. Its tiny temperature variations, fluctuations of about 1 part in 100,000, encode information about the composition, geometry, and early history of the universe. It is the oldest light we can see, and it surrounds us completely, right now. Gravity waves from black hole mergers ripple through the fabric of space-time. When two black holes spiral toward each other and merge, they release an enormous amount of energy in the form of gravitational waves, ripples in the curvature of space-time itself. These ripples travel outward from the merger at the speed of light, distorting distances ever so slightly as they pass. In 2015, the LIGO detector in the United States detected gravitational waves for the first time from the merger of two black holes about 1.3 billion light-years away. The distortion they caused in the detector was smaller than 1,000th the diameter of a proton. This detection represented a new way of listening to the universe, not through light, but through the vibrations of space-time itself. Since then, dozens more detections have been made, opening a gravitational wave astronomy that was previously impossible. The universe has exactly the right properties for stars and planets to exist. This is sometimes called the fine-tuning problem. The fundamental constants of nature, the strength of gravity, the mass of electrons and protons, the force binding atomic nuclei together, are fixed at values that, had they been even slightly different, would have produced a universe without stars, atoms, or chemistry. A slightly stronger gravity would have caused the universe to collapse back on itself before stars formed. A slightly weaker strong nuclear force would have prevented hydrogen from fusing into helium, and stars would never have ignited. Whether this reflects a deeper principle we haven't yet discovered, or the selection effect of the fact that only such a universe could be observed, remains one of the most profound open questions in all of science. The universe, at its deepest level, seems arranged for complexity. Hydrogen and helium make up about 98% of all ordinary matter in the universe. The two lightest elements dominate the cosmos. Hydrogen, the simplest element with a single proton and electron, accounts for roughly 73% of all ordinary matter. Helium accounts for about 25%. All the other elements, carbon, oxygen, nitrogen, iron, silicon, calcium, gold, and everything else on the periodic table, make up only about 2% of the universe's ordinary matter content. These heavier elements were forged in the nuclear furnaces of stars and scattered by stellar winds and supernova explosions across billions of years. Every heavy atom in your body is a tiny piece of this 2%, assembled by the remarkable process of stellar nucleosynthesis across multiple generations of stars that lived and died before the solar system formed. Atoms are almost entirely empty space. The nucleus of an atom, containing protons and neutrons, occupies only about 1/trillionth of an atom's volume. If an atom were expanded to the size of a football stadium, its nucleus would be roughly the size of a marble at the center. The electrons orbit far out in the surrounding space, but interact with the atom's interior through electromagnetic forces rather than physical contact. The apparent solidity of matter, the resistance you feel when you touch a table, the firmness of the ground beneath you, comes not from physical contact between nuclei, but from electromagnetic repulsion between electron clouds. The universe is composed of objects that are almost entirely empty, held together by forces that never touch. Quantum mechanics governs the smallest scales of the universe in ways that have no intuitive analogy. At the level of electrons, photons, and quarks, the familiar rules of classical physics break down. Particles do not have definite positions and velocities simultaneously. This is not a limitation of measurement, but a fundamental feature of reality described by the Heisenberg uncertainty principle. Quantum objects exist in superpositions of states until measured. Entangled particles can have correlated properties regardless of the distance between them, in a manner that seems to transcend space. Quantum tunneling allows particles to cross energy barriers they should not be able to cross classically, enabling nuclear fusion in stars and chemical reactions in biology. Every transistor, laser, and modern electronic device operates on quantum principles. The universe at its smallest scale behaves in ways that are deeply strange and irreducibly probabilistic. Yet the mathematics of quantum mechanics makes predictions of extraordinary accuracy. The Standard Model of Particle Physics describes 17 fundamental particles. These 17 particles, 6 quarks, 6 leptons including the electron, 4 force-carrying bosons, and the Higgs boson, are the building blocks of all known matter and the carriers of the forces that govern it. 3 of the 4 fundamental forces of nature are described within the Standard Model: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Gravity, The fourth fundamental force remains outside the standard model, described instead by general relativity. Reconciling quantum mechanics with general relativity into a single coherent theory of quantum gravity remains the deepest unsolved problem in fundamental physics. The standard model, despite its remarkable success, is incomplete. It accounts for about 5% of the universe's total energy content and has nothing to say about the dark matter and dark energy that make up the rest. The Higgs boson gives other particles their mass. Until 2012, the Higgs boson was the last undetected particle predicted by the Standard Model. It was discovered at the Large Hadron Collider at CERN in Geneva, confirming a mechanism proposed in the 1960s. The Higgs field permeates all of space, and particles acquire mass through their interaction with this field. Particles that interact strongly with the Higgs field are heavy. Particles that interact weakly are light. Photons do not interact with the Higgs field at all, which is why they are massless and travel at the speed of light. Without the Higgs mechanism, all fundamental particles would be massless and would travel at the speed of light, and atoms, chemistry, and matter as we know it could not exist. The discovery of the Higgs boson was the confirmation of a process that makes the material universe possible. Cosmic rays bombard Earth from all directions, continuously. High-energy particles, mostly protons and atomic nuclei, but also electrons and other particles, stream through space at nearly the speed of light, arriving at Earth from every direction. These are cosmic rays, and they originate from a variety of sources: solar flares, supernova remnants, active galactic nuclei, and possibly sources not yet identified. When cosmic rays strike Earth's upper atmosphere, they initiate cascades of secondary particles that rain down to the surface. Even at sea level, cosmic rays pass through your body roughly once per second. The most energetic cosmic rays detected have energies vastly exceeding anything achievable in human-built particle accelerators. Where these ultra-high-energy cosmic rays originate is one of the outstanding mysteries of astrophysics. The universe contains more atoms than could ever be counted. Estimates of the number of atoms in the observable universe range from approximately 10 to the power of 78 to 10 to the power of 82, numbers so large they defy any ordinary analogy. If you counted 1 atom per second from the moment of the Big Bang to now, you would have counted roughly 4 times 10 to the power of 17 atoms. At that rate, counting all the atoms in the observable universe would take more time than the universe has existed, multiplied by itself, and many more times over. These atoms are distributed across galaxies, stars, gas clouds, and the vast spaces between them. And somewhere within that unimaginable abundance, a particular arrangement of atoms on a small blue planet is falling gently asleep. There are more stars in the observable universe than grains of sand on all of Earth's beaches. This comparison has become famous for a reason. It gives scale to an otherwise abstract number. Estimates of the total number of stars in the observable universe range from 10 to the power of 23 to 10 to the power of 24. The number of grains of sand on all Earth's beaches is estimated at around 7.5 times 10 to the power of 18. Stars outnumber sand grains by a factor of many thousands. Most of these stars are invisible to the naked eye. The roughly 5,000 stars visible without a telescope on a clear night represent a tiny fraction of one galaxy. The night sky we see is not the universe. It is the faintest hint of one corner of one galaxy in a cosmos of unimaginable depth. Many of those stars have planets. For most of human history, we could only speculate about whether other stars had planets. Since the 1990s, astronomers have confirmed thousands of planets orbiting other stars, called exoplanets, and statistical analysis suggests that virtually every star has at least one planet on average. Our galaxy alone may contain hundreds of billions of planets. Many of them orbit in the habitable zones of their stars, where liquid water might exist on their surfaces. Some have been found with sizes and orbital periods similar to Earth's. The discovery that planets are common, not rare cosmic accidents, transforms the question of whether life exists elsewhere from philosophical speculation into a question of probability and statistics. We are not alone in having a world. Whether we are alone in other senses remains unknown. The nearest star system to our own is about 4.2 light-years away. Proxima Centauri, a small red dwarf, is the closest individual star to the Sun. At the speed of the Voyager 1 spacecraft, currently the fastest human-made object and the most distant, it would take approximately 74,000 years to reach Proxima Centauri. At the speed of light, the journey would take just over 4 years. A planet has been discovered orbiting Proxima Centauri within its habitable zone, called Proxima b. Whether it has an atmosphere, liquid water, or life is unknown. What makes this neighbor so fascinating is that it is our closest possible destination, and it remains, by any practical standard, essentially unreachable with current technology. The distances between stars are not just large. They are a fundamental feature of the universe that enforces an extraordinary solitude. The Milky Way is on a collision course with the Andromeda Galaxy. In approximately 4.5 billion years, our galaxy and its nearest large neighbor will collide and begin a merging process that will last for billions more years. This is not a distant threat. It is simply the next chapter in the gravitational history of the local group of galaxies. Stars in a galactic collision almost never hit each other directly because the distances between individual stars are so vast. But the shapes of both galaxies will be dramatically distorted, long tidal tails will stream into space, and eventually the two systems will settle into a merged elliptical galaxy, sometimes nicknamed Milkomeda. When this happens, the night sky from any surviving planet in the merged system will be extraordinary, dominated by a blaze of stars and the vivid light of two interacting galactic cores. Our current night sky, seen from Earth, is a temporary arrangement. The sky is always changing, just on timescales beyond a human lifetime. The universe is getting lonelier over time. Because the expansion of the universe is accelerating, distant galaxies are being carried away from us at ever-increasing rates. Galaxies beyond a certain distance, the cosmic event horizon, will eventually recede faster than light can travel to us, making them permanently unreachable and eventually invisible. This does not violate the speed of light limit. It is space itself expanding, not objects moving through space. Over trillions of years, the local group of galaxies will remain gravitationally bound, while the rest of the universe becomes increasingly isolated from us. In an unimaginably distant future, the merged Milky Way and Andromeda galaxies may be the only galaxies visible from within, surrounded by a dark and empty void where 2 trillion galaxies once blazed. The universe is not eternal and static. It is unfolding toward increasing quietness. Some galaxies have already stopped forming new stars, called red and dead galaxies. These systems burned through their gas supply long ago in intense bursts of star formation and now contain mostly older, redder stars. Without fresh gas, no new stars ignite. The galaxy still shines, beautifully, sometimes, but it is the light of an aging population. Over hundreds of billions of years, even these ancient stars will exhaust their fuel and fade. A red and dead galaxy is a snapshot of what most large galaxies may eventually become. Luminous, but no longer generative. Bright with memory rather than fresh creation. The universe as a whole has been forming stars more slowly since roughly 10 billion years ago. The great epic of star formation is past its peak. We live in the cosmos Middle Age, looking back at a more fertile time. Time runs differently depending on gravity and velocity. Einstein's general and special theories of relativity predict that time is not universal. It passes at different rates depending on how fast you are moving and how strong the gravitational field is around you. A clock near a massive object runs slightly slower than one farther away. A clock moving at high velocity runs slower than one at rest. These are not effects of poor clock design. They reflect a genuine difference in the passage of time itself. GPS satellites in orbit must account for relativistic time dilation to maintain accuracy, without corrections for both special and general relativistic effects. GPS positioning would drift by several kilometers per day. Near a black hole, time dilation becomes extreme. An observer hovering just above the event horizon would age enormously slowly compared to an observer watching from a safe distance. Time, at its deepest level, is elastic. The universe may contain parallel realities we cannot access. Several interpretations of physics suggest the possibility that our observable universe is not alone. The many worlds interpretation of quantum mechanics proposes that every quantum measurement causes the universe to branch into multiple versions, each outcome occurring in a different branch. Eternal inflation, a theory of the universe's earliest expansion, suggests that our Big Bang was one of many, each producing a separate region of space-time with potentially different physical laws. The string theory landscape proposes an enormous number of possible universes with different values of the fundamental constants. None of these ideas has been observationally confirmed, and some may be untestable in principle. But they are taken seriously by physicists because they arise naturally from the mathematics of our best theories. Whether we exist in a single universe or one of many, the question itself reveals how far our imagination of the cosmos has come from the first humans who looked up and wondered about the sky. There is a theoretical temperature that represents the hottest possible state of matter. Called the Planck temperature, it is approximately 1.4 times 10 to the power of 32 degrees Celsius, a number so large that any analogy fails. Below this temperature, matter and energy behave in ways our current physics can describe. Above it, the laws of physics as we understand them break down completely. The universe reached this temperature in the first 5 times 10 to the power of negative 44 seconds after the Big Bang, a moment called Planck time. Everything before that moment is currently beyond our ability to describe or even theorize about with any confidence. It is a wall in our understanding, marking the edge of what our current tools can reach, a reminder that the universe keeps secrets in plain sight. The night sky is not perfectly dark, it is faintly glowing with ancient starlight. If the universe were infinitely old, infinitely large, and uniformly filled with stars, the night sky would blaze as brightly as the surface of a star in every direction. The fact that it is dark instead, Olber's paradox, posed in the 19th century, is explained by the finite age and expanding nature of the universe. Light from very distant stars has not yet had time to reach us, and the expansion of space stretches starlight to longer wavelengths, reducing its energy. But even in the darkest patch of sky, there is light, the diffuse glow of billions of unresolved galaxies below the threshold of visibility, the cosmic microwave background, and starlight scattered through intergalactic space. The darkness between the stars is never truly empty. It holds the faintest possible whisper of everything. Stars are mostly held together by their own gravity, balanced against the outward pressure of nuclear fusion. A star is not simply burning like a campfire. It is a dynamic equilibrium between two opposing forces. Gravity pulls every part of the star toward its center. The energy released by nuclear fusion in the core pushes outward as radiation pressure and thermal pressure. When these forces balance exactly, the star maintains its size and shines steadily for millions or billions of years. When the fuel in the core runs out, the balance is broken. Gravity wins, and the star begins to change, swelling into a giant, collapsing to a white dwarf or neutron star, or exploding as a supernova. The life of a star is the story of this balance being maintained and eventually lost. Our sun has been in this equilibrium for 4.6 billion years and will remain so for roughly 5 billion more. The universe appears to have no center. This is one of the stranger and more disorienting facts about the cosmos. In an ordinary explosion, material expands outward from a central point. But the Big Bang was not an explosion in space. It was an expansion of space itself. Every point in the universe moved away from every other point, which means that from every galaxy, the universe appears to be expanding outward in all directions equally. There is no special location at the center of this expansion. Every observer, no matter where in the universe they are located, sees the same thing. All other galaxies receding in every direction at a rate proportional to distance. The universe has no edge, no center, and no outside. It is a structure that contains everything, and within which every point is equivalent to every other. The fate of the universe is uncertain, but its most likely endings are known. If dark energy continues to push expansion at the current rate, the universe faces a slow fade called the Big Freeze or heat death, a state of maximum entropy in which all stars have burned out. Black holes have evaporated through Hawking radiation over unimaginably long time scales, and the cosmos has settled into a cold, dark, nearly featureless state. Alternatively, if dark energy strengthens over time, the expansion could accelerate to the point where it tears apart galaxies, solar systems, and eventually atoms, in an event called the Big Rip. A third possibility, the Big Crunch, would require dark energy to eventually reverse into attraction, causing the universe to collapse back on itself. But current observations make this unlikely. Whatever awaits, the universe has trillions of years ahead of it, and we are in one of its most richly structured and luminous chapters. The universe is transparent to neutrinos. Every second, roughly 65 billion neutrinos from the sun pass through every square centimeter of your body facing the sun, and most of the rest of your body as well, since neutrinos pass through Earth almost without interaction. Neutrinos are produced in nuclear reactions and travel through space and matter nearly unimpeded. They interact only through the weak nuclear force and gravity, making them nearly impossible to detect. To stop just half of a beam of neutrinos, you would need a wall of lead extending from here to the nearest star. The universe is essentially transparent to these ghostly particles, and they carry information from deep inside stars and from the cores of supernovae that is inaccessible through any other means. Vast underground detectors filled with pure water or ice, like the ice cube detector in Antarctica, catch a few of the enormous flood that passes through every moment. The universe emerged from a quantum fluctuation, or something like one. Some cosmological models suggest that the Big Bang itself was the result of a quantum event, specifically, a quantum tunneling of the universe from a state of nothing to a state of something. In quantum mechanics, tunneling allows particles to cross energy barriers they classically could not. On the cosmological scale, This concept has been extended to suggest that the universe itself could have arisen from a quantum fluctuation in a pre-existing space-time, or from nothing at all, in the sense that quantum mechanics permits certain physical processes to occur spontaneously. This is not a settled or universal interpretation, and the phrase "nothing" in cosmology has a specific technical meaning different from ordinary language. But the idea that the largest thing we know of might be the consequence of the smallest possible kind of event is one of the most extraordinary in all of science. Planets can exist without a star. Rogue planets, also called free-floating planets or orphan planets, are worlds that have been ejected from their parent solar systems and now drift alone through interstellar space. They form normally around stars, but are flung out by gravitational interactions with other planets or nearby stars. Once free, they travel through the galaxy without any sun to warm them. Their surfaces are cold and dark, but some may have thick atmospheres that retain residual internal heat. Some may even have subsurface oceans kept liquid by geological activity rather than stellar warmth. Estimates suggest that rogue planets may be extremely common, possibly more numerous than stars. The galaxy may be filled with dark, cold, lonely worlds traveling silently through the space between stars, carrying no light, but carrying the memory of systems from which they were born. Infrared telescopes reveal a universe invisible to ordinary eyes. Visible light is only a narrow slice of the electromagnetic spectrum. Infrared radiation, with longer wavelengths than visible light, is emitted by cool objects and can penetrate clouds of dust that block visible light. The James Webb Space Telescope, launched in 2021, observes primarily in infrared and has revealed galaxies from the first few 100 million years of the universe's existence. Galaxies that were previously hidden behind clouds of dust or too faint and too red-shifted to see invisible light. Webb has shown that some of the earliest galaxies were surprisingly large and well-formed, challenging some earlier models of how quickly structure can grow after the Big Bang. With every image from Webb, the universe becomes simultaneously more familiar and stranger. We see further back than ever before, and what we find continues to surprise. The universe had its golden age of galaxy formation about 10 billion years ago. Observations of distant galaxies, which are also ancient galaxies, since their light has been traveling for billions of years, show that the rate of star formation across the universe was much higher in the past than it is today. The peak era of galaxy building, when the most new stars per unit time were born across all galaxies combined, occurred when the universe was roughly 3 to 4 billion years old. Since then, star formation rates have declined steadily. The universe of today is quieter than the universe of the past. Galaxies that were once blazing with the light of millions of new stars each year now form only a small fraction of that. We live in a cosmos past its most frenetic creative period, still magnificent, but slowing toward an eventual stillness. The universe is electrically neutral on large scales. Although matter is made of charged particles, positively charged protons and negatively charged electrons, the universe maintains an almost perfect balance between positive and negative charges on every large scale we can measure. If this balance were even slightly off, electromagnetic forces would vastly overpower gravity on cosmic scales, and the universe would behave in completely different ways. The balance is so precise that it appears to be a fundamental feature of the physics of the early universe rather than a coincidence. This neutrality is one of the reasons gravity is the dominant force on astronomical scales, even though electromagnetism is a far stronger force at close range. On the scale of a planet or a galaxy, charges cancel, and gravity, though weak, rules unchallenged. The universe may be undergoing an eternal inflation that never truly stopped. In some versions of inflationary cosmology, the rapid expansion that occurred in the universe's first moments never entirely ceased. Instead, inflation continued in regions of space-time that never reheated into ordinary matter and energy, while in other regions, like our own, inflation ended and the familiar universe formed. In this picture, new bubble universes nucleate continuously from the inflating background, each potentially with different physical laws and constants. Our observable universe would be one such bubble, surrounded by an eternally inflating background that we can never observe. This is the multiverse hypothesis in one of its most theoretically developed forms. It is speculative and may remain untestable, but it is taken seriously because it arises from well-motivated physics and makes the existence of our particular universe, with its peculiar constants, less surprising rather than more. Even empty space is not truly empty. Quantum field theory predicts that a perfect vacuum, a region of space entirely devoid of matter and radiation, is nonetheless filled with quantum vacuum energy. Virtual particle-antiparticle pairs continuously pop into existence and annihilate in times so brief that they cannot be directly detected, but their presence has measurable effects. The Casimir effect, measured in laboratory experiments, arises from the suppression of some virtual particle fluctuations between two closely spaced conducting plates, resulting in a tiny but measurable attractive force between them. Hawking radiation, the theoretical process by which black holes slowly evaporate, is thought to arise from vacuum fluctuations near the event horizon. The vacuum is not nothing. It is a seething, probabilistic sea of energy from which matter itself ultimately springs. Space is alive with something even in its emptiest state. Galaxies are surrounded by vast halos of dark matter far larger than their visible parts. When astronomers measure how fast stars and gas orbit within galaxies, the visible mass of the galaxy does not provide enough gravity to explain the observed speeds. Outer regions orbit too quickly, as though there were more mass there than we can see. The standard explanation is dark matter, invisible mass that forms a roughly spherical halo extending far beyond the visible disk of the galaxy. This dark matter halo may be 10 to 30 times the mass of the visible galaxy it surrounds and may extend for hundreds of thousands of light years beyond its visible edge. Dark matter appears to be made of particles that interact through gravity but not through electromagnetism, meaning they neither emit nor absorb light. Despite decades of searching with the world's most sensitive detectors, the identity of dark matter particles remains unknown. What we call a galaxy is in reality the luminous core of a far larger, invisible structure. The first light in the universe was not visible to human eyes. When the cosmic microwave background was released at 380,000 years after the Big Bang, the universe was much hotter than it is today. The radiation released at that moment was in the infrared to visible range. But over 13.8 billion years of cosmic expansion, that light has been stretched, redshifted, to microwave wavelengths, well below the range of human vision. The CMB today has a temperature of about 2.7 degrees above absolute zero and permeates all of space. When you look at the static on an old analog television set, a small fraction of what you see is this ancient light, now in microwave form, received by the antenna from the sky. The universe's first light is still among us, invisible to the eye but measurable, detectable, and carrying a detailed record of conditions shortly after creation. The universe contains structures called magnetars, the most powerful magnetic objects known. Magnetars are a rare type of neutron star with magnetic fields a quadrillion times stronger than Earth's. If a magnetar were positioned halfway between Earth and the Moon, its magnetic field would be strong enough to pull the iron from your blood cells at that distance. These extreme magnetic fields arise during the collapse of massive stars and are thought to power periodic bursts of intense X-ray and gamma-ray radiation observed from distant corners of the galaxy. Magnetars are short-lived. Their intense fields decay over thousands of years, and they may generate the most energetic electromagnetic events in the universe aside from the Big Bang itself. They represent a state of matter and energy so extreme that studying them probes physics impossible to reproduce in any laboratory. There may be a shadow universe of antimatter that we have never encountered. For every type of particle in the Standard Model, there is a corresponding antiparticle with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy. The puzzle is that the Big Bang should have produced matter and antimatter in equal quantities. Had that happened, they would have annihilated each other completely, leaving a universe of pure energy and no matter. The fact that we exist in a matter-dominated universe means that slightly more matter was produced than antimatter, by about 1 part in a billion, for reasons that remain one of the deepest unsolved problems in physics. That tiny asymmetry is why we are here. The rest of the matter and antimatter destroyed each other, and what was left became everything: galaxies, stars, planets, and the atoms of every living thing. There are more possible ways to arrange atoms in a human body than there are atoms in the observable universe. The human body contains roughly 7 times 10 to the power of 27 atoms. The number of ways those atoms could theoretically be arranged, including arrangements that do not produce a functioning body, is an astronomically larger number. This is not just philosophical. It is a reflection of the combinatorial richness of complex matter. The specific arrangement of atoms that constitutes you is, statistically speaking, unique not just in this moment, but in all of cosmic history. The universe has never made this exact configuration before and, in all probability, never will again. You are a temporary, specific, irreplaceable arrangement of the universe's matter, briefly conscious of its own existence in a cosmos that has been running experiments in complexity for 13.8 billion years. Some stars explode in a peculiar way called apparent stability supernova. The most massive stars, those more than roughly 130 times the mass of the Sun, can die in an unusually violent type of explosion caused by a quantum mechanical process. In their cores, gamma rays become energetic enough to spontaneously produce electron-positron pairs. This process absorbs energy that would otherwise support the star against gravity, causing the core to contract rapidly. The contraction heats the core further, runaway thermonuclear burning ignites, and the entire star can be completely disrupted in the explosion, leaving no remnant at all, not even a neutron star or black hole. The explosion releases 5 to 10 times more energy than a typical core collapse supernova, briefly lighting up as brilliantly as an entire galaxy. These extraordinary events may have been common in the early universe among the first generation of enormous metal-poor stars. The observable universe has a horizon beyond which nothing can ever reach us. As the universe expands, there is a boundary called the cosmic event horizon, the distance beyond which light emitted today will never reach us, even given infinite time. This is different from the observable universe's edge, which marks the farthest light that has already reached us. The cosmic event horizon is determined by the current rate of expansion. If a galaxy is far enough away, the expansion of space between us will always outpace the light it sends toward us, and no signal will ever arrive. This means that the universe we can ever observe or interact with is finite and shrinking, in the sense that more and more galaxies are permanently crossing beyond this horizon. The universe is not withholding information. It is simply a consequence of geometry and the nature of an accelerating expansion. White dwarfs will be the final luminous remnant of most stars. When the sun eventually exhausts its fuel and sheds its outer layers as a planetary nebula, the core left behind will be a white dwarf, a dense, Earth-sized object composed mostly of carbon and oxygen, hot at first, but no longer generating energy through fusion. White dwarfs cool gradually over trillions of years. Current calculations suggest that the universe is not yet old enough for any white dwarf to have cooled completely. The very oldest white dwarfs we can observe are still faintly warm. In the distant future, white dwarfs will cool to black dwarfs, objects at the temperature of the surrounding space, dark and cold. But the time required for a white dwarf to cool to a black dwarf is longer than the current age of the universe. No black dwarfs yet exist. They are the universe's promise to its most distant future. Light from stars actually comes from millions of years below the surface. The photons produced in the sun's core by nuclear fusion do not travel straight outward into space. They are absorbed and re-emitted so many times in the dense plasma of the solar interior that the average photon takes between 10,000 and 170,000 years to travel from the core to the surface, a journey that takes only about 8 minutes once the photon escapes. This slow, random walk through the sun is caused by the extraordinary density of the solar plasma, in which light can barely travel a millimeter before being absorbed and re-emitted in a random new direction. The sunlight that warms Earth today was created in nuclear fusion reactions that occurred tens of thousands of years ago, when our ancestors were using stone tools. The sun's light reaches us with a built-in delay from deep in its own history. Galaxies cluster in groups, and those groups cluster in superclusters. Our own Milky Way is part of the local group, a collection of more than 50 galaxies gravitationally bound together, dominated by the Milky Way and Andromeda. The local group is itself part of the Virgo supercluster, a vast assembly of galaxies spanning roughly 110 million light-years, containing more than 1,300 member galaxies. The Virgo supercluster is in turn embedded in an even larger structure called the Laniakea supercluster, identified in 2014, which spans roughly 520 million light-years and contains the mass of 100 million billion suns distributed across hundreds of thousands of galaxies. Laniakea means immeasurable heaven in Hawaiian. On the scale of Laniakea, our galaxy is a single grain of matter in a structure the size of a grain of rice compared to the Earth. The universe nests structures within structures, each enormous on the scale of anything below it. The universe is electrically neutral but permeated by magnetic fields. From the tiniest scales of atomic nuclei to the largest scales of galaxy clusters, magnetic fields thread through the cosmos. Planets, stars, galaxies, and galaxy clusters all generate magnetic fields, and even the vast spaces of the intergalactic medium appear to contain weak but measurable magnetic fields of uncertain origin. Some cosmologists speculate that there is a primordial magnetic field that permeates the entire universe, seeded during the very early moments of creation. These fields influence how cosmic rays travel, how galaxies form, and how matter is organized on large scales. Unlike gravity, which only attracts, Magnetic fields can both attract and repel, creating complex structures and channeling matter in ways that differ from purely gravitational behavior. The universe is threaded with magnetism at every level we can probe. Some stars in the Milky Way are older than 13 billion years. Our galaxy contains stars that formed in its earliest epochs, when the universe was only a few 100 million years old. These ancient stars, found mainly in the galactic halo and in globular clusters, have extremely low concentrations of heavy elements. Evidence that they formed before many generations of stars could enrich the galaxy with the products of stellar nucleosynthesis. Some individual stars have been identified that appear to be nearly as old as the universe itself. How they survived for so long while the galaxy around them was built, collided, and transformed is a remarkable aspect of stellar archaeology. These ancient stars are time capsules from the universe's earliest epoch, still burning quietly in a galaxy that has changed almost beyond recognition since they first ignited. The universe is capable of creating enormous structures in empty space. Observations of galaxy clusters and superclusters have revealed that the boundaries between voids are not sharp. They are connected by filaments, walls, and sheets of matter that form the cosmic web. Within galaxy clusters, the space between galaxies is filled with hot gas, sometimes called the intracluster medium, at temperatures of tens of millions of degrees, glowing in X-rays. This gas is more massive than all the visible stars in the cluster combined and has been heated by the gravitational energy of the cluster's formation and by energetic events like galaxy mergers and active black holes. Even the apparently empty spaces between galaxies are full of diffuse, hot, invisible matter. The universe at every scale has more in it than first appears. Sound cannot travel through outer space, but plasma waves can. The familiar concept of sound, compression waves moving through a medium, requires matter to propagate. In the near-perfect vacuum of outer space, there is not enough matter for sound waves to travel. But in the extremely hot, thin plasma of the early universe, acoustic waves did propagate through the primordial fluid, and the imprint of these ancient sound waves can still be seen today in the distribution of galaxies across the cosmos, a phenomenon called baryon acoustic oscillations. The preferred distance between galaxy concentrations, observable in surveys of the large-scale structure of the universe, reflects the size of these ancient acoustic waves, frozen into the distribution of matter when the early plasma cooled enough for atoms to form. The universe carries the echo of sound from an era when all of space was a single resonant medium. The Hubble constant describes the rate of the universe's expansion, and there is a mystery about its value. The Hubble constant is the number that tells us how fast the universe is expanding per unit distance. Galaxies farther away recede faster by a predictable ratio. Measurements of the Hubble constant from the cosmic microwave background, which samples the early universe, give a slightly different value than measurements made from nearby supernovae and Cepheid variable stars. This discrepancy, called the Hubble tension, is small in absolute terms but statistically significant, and it has resisted explanation for years. Either one or both methods have undetected systematic errors, or there is new physics between the early and late universe that we do not yet understand. The Hubble tension is currently one of the most hotly debated questions in cosmology, and its resolution may require a revision of our standard model of the universe. Binary star systems are more common than single stars. Most stars in the Milky Way, and presumably in other galaxies, are members of binary or multiple star systems, two or more stars orbiting their common center of mass. A significant fraction of stars are in binary pairs. Some are in triple or quadruple systems. The night sky we see is deceptive. Many of the bright points we see as single stars are in fact unresolved binary systems. Two or more stars so close together from our perspective that they appear as one. Binary systems have profound consequences. They can exchange mass, create exotic objects like millisecond pulsars and X-ray binaries, and produce the types of supernova used to measure cosmic distances. Even stars choose company in the universe more often than not. Solitude among stars, as among galaxies, is the exception rather than the rule. The universe was once hotter than 1 billion suns. In the first minutes after the Big Bang, the universe was so hot and dense that nuclear reactions were occurring throughout all of space. During this period, Big Bang nucleosynthesis, the proportions of hydrogen, helium, and trace amounts of lithium and deuterium were established. The process lasted only a few minutes before the universe expanded and cooled enough for the reactions to cease. The result was a universe composed of about 75% hydrogen and 25% helium by mass, with only trace amounts of anything else. This primordial composition is what stars were made from. Over billions of years, generations of stars have gradually enriched the universe with heavier elements. But even today, most of the universe's ordinary matter is still the primordial hydrogen and helium forged in those brief, brilliant first minutes. Quantum entanglement connects particles across any distance. One of the strangest predictions of quantum mechanics, and one of the most thoroughly confirmed by experiment, is entanglement. When two particles interact in certain ways, they can become entangled. Their quantum states are correlated such that measuring one instantly determines something about the state of the other, regardless of the distance separating them. This correlation persists even if the particles are separated by a room, a continent, or in principle the diameter of the observable universe. This was called spooky action at a distance by Einstein, who believed it must reflect some deeper classical reality. But experiments have repeatedly confirmed that quantum entanglement is real, and that it cannot be explained by any local hidden variable theory. No signal passes between the entangled particles. The correlation is not communication. It cannot be used to transmit information, but it is nonetheless a feature of reality that transcends ordinary space, a thread connecting particles across the universe in a way that has no precedent in classical physics. There are stellar remnants inside nebulae that are the corpses of exploded stars. When a massive star explodes as a supernova, it leaves behind both a remnant, the neutron star or black hole at the center, and a vast expanding shell of gas and debris called a supernova remnant. These remnants can glow for thousands of years as the expanding shock wave heats interstellar gas, creating some of the most beautiful structures in the sky. The Crab Nebula, visible to small telescopes, is the remnant of a supernova observed and recorded by Chinese astronomers in 1054 AD. At its center pulses a neutron star, the Crab Pulsar, rotating 30 times per second. The nebula is still expanding at about 1,500 kilometers per second, a slow-motion explosion still visible nearly 1,000 years later. Supernova remnants are not just beautiful. They are the mechanism by which heavy elements are distributed into the interstellar medium, eventually becoming the raw material for new stars, planets, and life. The universe may have undergone a period of extremely rapid inflation in its first moments. The theory of cosmic inflation proposes that in the first tiny fraction of a second after the Big Bang, far less than a trillionth of a second, the universe underwent a phase of extraordinarily rapid exponential expansion, growing by a factor of at least 10 to the power of 26 in an almost immeasurably brief time. This inflation would have smoothed out any initial irregularities in the universe's density and geometry, explaining why the cosmic microwave background is so uniform in all directions and why the universe appears flat on large scales. Inflation would also have magnified quantum fluctuations to macroscopic scales, seeding the small density variations that eventually grew into galaxies and the cosmic web. Cosmic inflation is not a directly confirmed theory, but it accounts for several otherwise puzzling features of the observable universe with remarkable elegance. The nearest large galaxy to the Milky Way contains 1 trillion stars. The Andromeda Galaxy, about 2.5 million light-years away, is the largest member of the local group and the closest large galaxy to our own. It contains roughly 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion. Andromeda is also orbited by numerous satellite galaxies and has a complex history of mergers and interactions that have shaped its current structure. On a very dark night, far from light pollution, Andromeda is faintly visible to the naked eye as a smudge in the constellation Andromeda, the most distant object visible without a telescope, a trillion-star galaxy that fits within the angular size of the full moon as seen from Earth. That tiny blur of light has been traveling for 2.5 million years. Each photon from that smudge in the sky began its journey 2.5 million years ago, in a galaxy full of stars that have aged 1 million times faster than any human civilization. Cosmic timescales make human history almost unmeasurably brief. The universe is 13.8 billion years old. Modern humans have existed for about 300,000 years, roughly 0.002% of the universe's age. Recorded human history spans perhaps 5,000 years, 0.00036% of cosmic time. The entire span of human civilization since the invention of writing, the development of agriculture, the building of the pyramids, the rise and fall of empires, the invention of science and democracy, and art and music, all of it fits within a period so brief on cosmic timescales that it would not register on a graph of the universe's history unless you zoomed in many orders of magnitude. This is not a diminishment of human significance. It is a reminder that the universe is patient beyond all imagining, that what we call history is the very beginning of something, and that there is more time ahead than behind. Certain stars orbit the Milky Way's central black hole at tremendous speeds. The stars orbiting nearest to Sagittarius A*, the supermassive black hole at the Milky Way's center, move at extraordinary speeds. One star, designated S2, completes one orbit around Sagittarius A* in just under 16 years, an orbit comparable in size to the orbit of Uranus around the Sun. At the closest point in this orbit, S2 travels at roughly 8,000 kilometers per second, about 2.7% of the speed of light. Astronomers at the Max Planck Institute for Extraterrestrial Physics tracked S2's orbit over more than 27 years, confirming the mass of Sagittarius A* to high precision and providing a direct test of Einstein's general relativity in the strong gravity regime near a supermassive black hole. These orbiting stars are essentially test particles in one of the most extreme gravitational environments in the local universe. The universe's largest explosions are gamma-ray bursts. Gamma-ray bursts are brief but extraordinary flashes of gamma-ray radiation, the most energetic electromagnetic events known in the universe since the Big Bang. Long gamma-ray bursts, lasting from a few seconds to several minutes, are associated with the collapse and explosion of massive stars and can briefly outshine their entire host galaxies. Short gamma-ray bursts, lasting less than 2 seconds, arise from the merger of neutron stars or a neutron star and a black hole. In either case, the energy released in a gamma-ray burst in just seconds can exceed the total light output of the Sun over its entire 10 billion-year lifetime. If a gamma-ray burst were directed at Earth from within about 8,000 light-years, it could strip away the ozone layer on the side facing it. Most occur at cosmological distances and pose no threat, but they reveal the extreme violence of which the universe is still capable. Life on Earth is made of atoms forged in the stars. Every element heavier than hydrogen and helium. Every carbon atom in your DNA. Every oxygen atom you breathe. Every calcium atom in your bones. Every iron atom in your blood was synthesized inside a star that died before the solar system formed. These atoms were scattered into space by stellar winds and supernova explosions, drifted as part of an interstellar cloud for millions of years, and eventually became part of the nebula from which the Sun and solar system collapsed. You are not separate from the universe. You are the universe in one of its more organized and temporarily self-aware configurations. The atoms in your left hand likely came from a different star than the atoms in your right. The stardust that formed the Earth has been assembled into oceans, continents, and living things, and some fraction of it has arranged itself, for a brief cosmic moment, into something that reads and wonders and sleeps. The Sun is traveling through the Milky Way at about 220 kilometers per second. The solar system orbits the center of the Milky Way on a roughly circular path, completing one full revolution every 225 to 250 million years, the cosmic year. At its speed of about 220 kilometers per second relative to the galactic center, the Sun covers roughly 19 million kilometers per day on its galactic journey. Over the entire age of the solar system, it has completed about 20 revolutions. The galactic neighborhood through which the Sun currently passes is known as the Orion Arm, a minor spur of the Milky Way between two major spiral arms. In the past 4.6 billion years, the solar system has traveled through regions of higher and lower star density, through galactic spiral arms, and through differing concentrations of interstellar gas and cosmic rays. Our location in the galaxy at any given time is not fixed. It is a point on an orbit, a traveler in a larger orbit within a larger orbit. There is a place in the sky where the universe's expansion is clearly visible. By plotting the recession speeds of thousands of galaxies against their distances, astronomers see a clear linear relationship. The farther a galaxy is, the faster it is receding. This is expressed by Hubble's law, first formulated by Edwin Hubble in 1929 based on observations from Mount Wilson Observatory. This relationship, velocity proportional to distance, is exactly what would be expected if space itself were expanding uniformly. Any observer anywhere in the universe would see the same relationship, because the expansion is not centered anywhere. It is a property of the space between every pair of points simultaneously. The universe's expansion is not visible in the night sky to the naked eye. It operates only on scales larger than galaxies. But it is as real as gravity, as pervasive as the CMB, and as fundamental to the nature of the cosmos as the speed of light. Some light we see left its source before Earth existed. The Sun and Earth formed about 4.6 billion years ago. Many of the stars visible in the night sky are thousands or millions of light years away, meaning the light we see from them left before our planet formed. The Andromeda Galaxy's light has been traveling for 2.5 million years, since before early members of the genus Homo walked the Earth. Some of the galaxies visible through large telescopes are so distant that their light left them more than 9 billion years before the solar system existed. Every time you look at the sky, you look at light that has crossed unimaginable distances and ages to reach your eyes. The night sky is not a static backdrop. It is a record, a library, a layered history of a universe in motion. What you see when you look up is not where those things are. It is where they were. Radio astronomy has revealed a universe invisible to optical telescopes. The universe emits radiation across the entire electromagnetic spectrum, not just invisible light. Radio astronomy, developed in the mid-20th century, has revealed phenomena that would have been invisible to optical telescopes. Pulsars, quasars, the cosmic microwave background, hydrogen gas in distant galaxies, and the molecular clouds where stars are born. The Very Large Array in New Mexico consists of 27 radio dishes that work together to image the sky with extraordinary resolution. Radio waves from pulsars have been used to test general relativity with higher precision than almost any other method. The methanol and water masers found in star-forming regions, natural laser-like amplifiers of microwave radiation, mark sites of intense stellar birth. The universe speaks in many wavelengths, and radio astronomy taught us to listen in ways that transformed our understanding of nearly everything. There is a fundamental limit to how much information can be stored in a region of space. The Beakenstein bound, derived from the physics of black holes and entropy, sets an upper limit on the amount of information that can be contained within a given volume of space with a given amount of energy. This suggests that the universe, at its deepest level, may be fundamentally digital, composed of discrete units of information rather than continuous fields. The holographic principle, a concept arising from string theory and black hole thermodynamics, goes further. It proposes that all the information about the interior of a three-dimensional volume can be encoded on its two-dimensional boundary, like the information in a hologram. If the holographic principle applies to the universe as a whole, then our three-dimensional experience of space may in some sense be a projection of information encoded on a distant two-dimensional surface. This idea is speculative, but it arises from real mathematics and real physics, and its implications for the nature of space, time, and information are profound. The concept of now is different for every observer in the universe. Special relativity shows that simultaneity is relative. Two events that are simultaneous for one observer may not be simultaneous for another observer moving at a different velocity. There is no universal present moment that applies across the cosmos. The question, what is happening right now in the Andromeda Galaxy, has no unique answer in physics. It depends on the reference frame of the observer asking it. For observers moving at different velocities, the ordering of causally disconnected events can differ. This does not mean time does not exist. It means that time is not a universal background against which events occur, but a local property of each observer's experience. The universe is not playing out on a single cosmic clock. Every point in the universe carries its own local time, shaped by its motion and the gravity around it. The universe appears to be nearly perfectly flat in its geometry. In general relativity, the geometry of space can be curved. It can be positively curved like the surface of a sphere, where parallel lines eventually meet, negatively curved like a saddle, where parallel lines diverge, or flat, where parallel lines remain parallel. Observations of the cosmic microwave background have measured the geometry of the observable universe with high precision and found it to be extremely close to flat, within about 0.4% of perfect flatness. This has implications. A flat universe is consistent with being spatially infinite, extending without limit in all directions. It also agrees with what inflationary models predict. The rapid expansion of the early universe would have stretched any initial curvature to near perfect flatness, just as the surface of a balloon appears flat when the balloon is inflated enormously. We appear to inhabit a flat, probably infinite universe. The oldest light in the universe carries the seeds of everything that exists. The tiny temperature variations in the cosmic microwave background, variations of 1 part in 100,000, were the seeds from which all large-scale structure grew. Slightly denser regions attracted slightly more matter, which increased their density further, which attracted still more matter, an amplifying gravitational process operating over billions of years. What began as quantum fluctuations in the first moments after the Big Bang were magnified by inflation to macroscopic scales, imprinted on the CMB as these tiny temperature variations, and then amplified over billions of years by gravity into galaxy filaments, galaxy clusters, and all the structure of the cosmic web. The great voids and superclusters of today were the faintest possible fluctuations in a 380,000-year-old glow. Everything you see, every star, every galaxy, every structure in the universe, traces its origin to the quantum noise of the very first moment. The universe contains at least 17 known types of distinct astrophysical objects. From main sequence stars like the Sun to red giants, white dwarfs, neutron stars, pulsars, magnetars, black holes, quasars, blazars, Seyfert galaxies, starburst galaxies, elliptical galaxies, irregular galaxies, planetary nebulae, supernova remnants, globular clusters, and open clusters. The universe has organized itself into an extraordinary diversity of structures at every scale. Each type represents a different balance of forces, a different stage of evolution, or a different outcome of the same underlying physical processes playing out under different initial conditions. The variety of astrophysical objects is not random. It reflects the richness of physics when applied across vast ranges of mass, temperature, density, and time. The universe is not monotonous in its creativity. It experiments endlessly. The universe appears to be a vast processor of entropy. The second law of thermodynamics states that entropy, a measure of disorder or the number of possible arrangements of a system, tends to increase over time in any closed system. The universe began in an extraordinarily low entropy state at the Big Bang and has been increasing in entropy ever since. Stars, which concentrate energy and release it as radiation, are part of this entropy-increasing process. Life, which creates local order but dissipates larger amounts of energy, also increases total entropy. The universe is, in a sense, running down from the highly ordered, low-entropy state of the Big Bang toward the maximum entropy state of the distant future, a state of uniform temperature and no available energy. All of the structure, beauty, and complexity of the universe, including every star, planet, and conscious being, exists in the space between these two endpoints, in the long, luminous moment of maximum structure before the final equilibrium. There are stars forming tonight in the Orion Nebula, about 1,300 light-years away, in the same direction as the constellation Orion. A vast molecular cloud is currently in the process of forming hundreds of new stars. The Orion Nebula, visible as a faint smudge in Orion's sword on a clear night, is the nearest large star-forming region to Earth. Inside it, protostars are collapsing from clouds of gas and dust, surrounded by circumstellar disks from which planets may eventually form. Some of the stars being born there now may eventually host planetary systems. Some of those planets, in the fullness of time, might give rise to chemistry complex enough to be called life. The universe is still making new possibilities. Its creative epoch is not over. Stars are igniting tonight, 1,300 light-years away, in a cloud of gas that will give rise to suns that will outlive the solar system. the universe has made it possible for matter to know itself. In 13.8 billion years, the universe has gone from a hot, structureless plasma to a state where some of the matter within it can perceive the universe, form theories about its origins, measure its extent, and marvel at what it contains. This remarkable fact, that the cosmos has produced observers who can look back at the cosmos, is not a minor detail. It is among the most extraordinary things about the universe. Whether consciousness is common or rare, whether it persists or is fleeting, whether this particular form of awareness on this particular planet is unique or commonplace, none of that diminishes the extraordinary fact that the universe has arrived at self-awareness at least once. In the atoms of your body, in the patterns of your thought, in the curiosity that drew you to wonder about the cosmos at all, the universe is looking at itself through borrowed eyes. Some of the oldest structures in the Milky Way are globular clusters. Globular clusters are dense, spherical collections of stars, anywhere from tens of thousands to several million stars packed into a region just a few hundred light-years across. They orbit the Milky Way in the galactic halo on long, looping paths, and many are among the oldest structures in the galaxy. Some contain stars more than 12 billion years old, formed before the Milky Way had its current spiral structure. These ancient stellar cities are visible to the naked eye. Omega Centauri, the largest and most massive globular cluster in the Milky Way, can be seen from the southern hemisphere as a faint star. It contains about 10 million stars packed into a sphere about 150 light-years in diameter. In the center of a globular cluster, stars are so densely packed that the night sky, seen from a planet there, would be ablaze with thousands of stars brighter than Venus appears from Earth. The universe has a preferred direction for time, but the fundamental laws of physics do not. This is called the arrow of time. The laws of physics at the fundamental level, quantum mechanics, general relativity, the Standard Model, are largely symmetric with respect to time. They work the same whether time runs forward or backward. Yet our experience of time has a clear direction. The past is fixed, the future is open, and processes generally evolve from order to disorder. The asymmetry of time we experience appears to arise from the low-entropy initial conditions of the Big Bang, rather than from any fundamental time asymmetric law of physics. The universe began in a very specific, ordered state, and has been relaxing toward disorder ever since. The arrow of time is thus cosmological in origin. We experience time as flowing in a particular direction because we are the descendants of an extraordinarily ordered beginning. There are places in the universe where gravity bends space so severely that even time stops. At the event horizon of a black hole, from the perspective of a distant observer, time appears to slow to a stop. An object falling into a black hole appears, from the outside, to asymptotically approach the event horizon, its clock slowing without limit. The object's image becomes increasingly redshifted and dim. From the perspective of the infalling object itself, it crosses the event horizon in finite time and continues toward the singularity, without noticing anything unusual at the moment of crossing. Inside the event horizon, if the physics we have applies there, the singularity is not a place but a moment, a future moment that lies in the direction of time itself, just as now lies in the direction of the future for observers outside. What happens at the singularity remains beyond the reach of current physics. The universe is transparent to most forms of radiation it produces. Visible light, radio waves, and some infrared radiation travel freely through the universe, allowing us to observe objects billions of light years away. But the early universe, before atoms formed, was opaque to light. And even today, The universe is not equally transparent at all wavelengths. X-rays and gamma rays are absorbed by dense matter, and very high-energy cosmic rays are scattered by the cosmic microwave background at great distances. The universe's transparency is not a simple given. It is the result of specific physical conditions that emerged at specific times in cosmic history. The fact that we can look across billions of light years and see the distant past is a consequence of the universe clearing its fog 380,000 years after the Big Bang. Before that clearing, no observer anywhere in the universe could have seen more than a short distance in any direction. The Moon is responsible for the stability of Earth's axial tilt. Earth's axial tilt, about 23.5 degrees, is responsible for the seasons. Without the stabilizing influence of the Moon's gravity, computer models suggest that Earth's tilt could vary chaotically over millions of years, swinging between nearly 0 and 85 degrees. Such dramatic changes would produce extreme climate swings. An axis nearly upright would create almost no seasons, while an extreme tilt would place the poles in direct sunlight for half the year. Mars, which has no large moon, has an axial tilt that has indeed varied widely over millions of years, contributing to dramatic changes in its climate. The Moon, formed in a giant impact with the proto-Earth roughly 4.5 billion years ago, acts as a gyroscopic stabilizer, keeping Earth's rotation steady and its seasons regular. The predictability of Earth's climate, so important for the evolution of complex life, is in part a legacy of that ancient collision. The universe's expansion is measured in an unexpected way, through the brightness of exploding stars. Type Ia supernovae, a specific class of stellar explosion that occurs when a white dwarf accretes enough mass from a companion star to exceed a critical threshold and explode, have a remarkably consistent peak luminosity. This makes them useful as standard candles. By comparing how bright they appear to how bright they intrinsically are, astronomers can calculate their distance. By measuring the distances and recession speeds of Type Ia supernovae at different distances, astronomers in 1998 discovered that the expansion of the universe is accelerating. This discovery, which earned the Nobel Prize in Physics in 2011, revealed the existence of dark energy and changed our picture of the universe's destiny. The most extreme events in stellar death, explosions bright enough to outshine entire galaxies, became the rulers astronomers used to measure the shape of the universe's future. The universe has produced objects that emit as much energy in a second as the sun does in a million years. Gamma-ray bursts and quasars represent the extreme upper end of astrophysical energy output, but even within the Milky Way there are extraordinary energy sources. Magnetars release more energy in 1/10 of a second than the sun does in 100,000 years. The jet from the active galactic nucleus M87, the galaxy whose black hole was imaged in 2019, can be seen in radio and X-ray, extending 5,000 light-years, carrying energy from one black hole across distances thousands of times larger than the Milky Way. The universe produces these extremes of energy not through any exotic process, but through the ordinary consequences of gravity and nuclear physics applied under the right conditions. Extremity in the universe is not a rarity. It is the natural expression of physics at scales and energies that arise routinely across 13.8 billion years of cosmic evolution. The universe contains regions where quantum effects and gravity both matter simultaneously. These conditions existed in the very early universe, at the Planck epoch, the first 5 times 10 to the power of -44 seconds after the Big Bang, and exist today inside black hole singularities. In these regimes, Neither quantum mechanics nor general relativity alone is sufficient. A theory of quantum gravity is needed. Several candidate theories exist: string theory, loop quantum gravity, causal set theory, but none has been confirmed experimentally. This gap in our understanding is not a minor footnote. The Planck epoch defines the very beginning of our universe and everything before it. Black hole singularities represent the ends of stars. A complete physical theory of the cosmos requires understanding these regimes, and we do not yet have one. The universe keeps a secret in its most extreme places, and we are still working to read it. The universe may have been preceded by other universes. Some cosmological models, including cyclic cosmology, propose that the Big Bang was not a unique beginning but one phase in an eternal cycle of expansions and contractions. In the cyclic model proposed by Paul Steinhardt and Neil Turok, two higher-dimensional membranes periodically collide, each collision producing what appears from within as a new Big Bang. Other models suggest that a collapsing universe could bounce into a new one, the Big Bounce. These hypotheses are difficult to test because any physical record of a universe before our own would have been largely erased in the transition. But some proponents have argued that certain patterns in the cosmic microwave background might carry signatures of a previous epoch. Whether our universe had a predecessor is unknown. Whether the question is even answerable is itself a deep scientific and philosophical issue. The universe may be less of a beginning than a chapter. Planets form from the debris of stellar birth. When a new star ignites, it is often surrounded by a disk of gas and dust left over from the collapse of the parent cloud. Within this protoplanetary disk, dust grains collide and stick together, gradually growing from micron-sized particles into centimeter-sized pebbles, then meter-sized rocks, then kilometer-sized planetesimals. Gravity then draws planetesimals together into planetary embryos, and those embryos grow by sweeping up material from the disk. The whole process can take from a few million to tens of millions of years. Planets form in the disk at characteristic distances from the star, with rocky planets closest to the star where the disk is too warm for ice to exist, and gas and ice giants forming farther out where ices can condense and provide the core around which gas accretes. Our solar system preserves a record of this process in its rocky inner planets, its gas giants, and its belt of asteroids between them. The universe contains enormous cosmic filaments of hydrogen connecting galaxies. Between galaxies, the cosmic web is threaded not only with dark matter, but with vast filaments of warm, hot intergalactic gas, primarily hydrogen, connecting galaxy clusters like the threads of a spider's web. This material, called the warm, hot intergalactic medium or WIM, may contain a significant fraction of all the ordinary matter in the universe. It is extremely diffuse, less dense than the best vacuum achievable in a laboratory, but the filaments extend for millions of light years and carry the raw material that galaxies draw in to fuel future star formation. The WIM is nearly invisible in most wavelengths, but can be detected in soft X-rays and through the absorption of ultraviolet light from background quasars. The space between galaxies is not empty. It is a faint, diffuse, vast sea of the universe's most abundant element, drifting through the architecture of the cosmic web. The universe produced its first heavy elements in the deaths of the earliest stars. Population 3 stars, the first generation of stars, contained no elements heavier than helium. When they died in explosions of extraordinary violence, often as parent stability supernovae, they scattered the first carbon, oxygen, nitrogen, and heavier elements into the surrounding gas. These elements became part of the next generation of stars, slightly enriching them above the primordial composition. Each subsequent generation enriched the galaxy further. The cumulative record of this enrichment is preserved in the spectra of stars of different ages, showing a clear progression from the metal-poor ancient stars to the more metal-rich younger ones. This is stellar archaeology. By measuring the composition of old stars, we read the story of how the universe gradually built up its periodic table, element by element, death by death, across billions of years. Even within the solar system, there are objects we have barely explored. The outer solar system is home to vast numbers of small icy bodies in the Kuiper Belt and the even more distant Oort cloud, a hypothetical shell of billions of comet nuclei extending up to a light year from the Sun. Pluto and its moons, visited by New Horizons in 2015, surprised scientists with active geology, young surfaces, and a complex atmosphere. Farther out, Arrokoth, a contact binary Kuiper Belt object visited in 2019, revealed how planetesimals gently combined in the early solar system. Most of the Kuiper Belt remains unvisited. The Oort cloud has never been directly sampled. Within our own cosmic backyard, worlds and processes remain almost entirely unknown. The universe hides mysteries not just at cosmological distances, but in the dark corners of our own stellar neighborhood, in objects so cold and distant they have barely been touched by light. Hawking radiation suggests that black holes are not truly permanent. Stephen Hawking proposed in 1974 that quantum effects near the event horizon of a black hole should produce a slow thermal emission of particles and radiation. This process, now called Hawking radiation, results from the behavior of quantum vacuum fluctuations near the event horizon. In a simplified picture, virtual particle-antiparticle pairs near the horizon can be separated by the gravitational potential, with one particle escaping as real radiation and the other falling inward. Over an extraordinarily long time, far longer than the current age of the universe for any black hole of stellar mass or larger, this process would cause a black hole to slowly evaporate and disappear. Hawking radiation has not been directly detected. It is too faint for any black hole we can observe, but it represents one of the most important theoretical predictions in modern physics, linking quantum mechanics, thermodynamics, and general relativity in a single result with profound implications for the ultimate fate of everything. The universe contains a whisper of primordial gravitational waves from inflation. If the theory of cosmic inflation is correct, the violent expansion of space-time in the universe's first moments would have generated a background of gravitational waves, ripples in space-time itself, that should still be present today, stretching across the universe and imprinted subtly on the cosmic microwave background. Detection of these primordial gravitational waves would be among the greatest confirmations in the history of cosmology. Experiments measuring the polarization of the CMB have been searching for this signal for years. In 2024, the BICEP/Keck array collaboration released new constraints on this signal, narrowing the allowed range. A confirmed detection would confirm that quantum fluctuations in the earliest moment of the universe were stretched by inflation into macroscopic gravitational waves that still gently ripple through all of space today. The universe's first cry, preserved in the fabric of space-time itself. The universe is still building. Galaxies are still forming. Stars are still igniting. Planets are still accreting. Somewhere in the universe right now, on a newly formed world orbiting a young star, the first organic molecules may be assembling in a warm ocean. The processes that led to life on Earth are not unique to Earth or to any particular moment in cosmic history. They are ongoing, and they are happening in countless places simultaneously. The universe did not make life once and move on. It makes the conditions for life continuously, in every galaxy, around every suitable star, wherever the right elements in the right concentrations find themselves in the right temperatures and environments. Whether those conditions always lead to life, we do not yet know. But the ingredients are everywhere. The universe has been generous with the raw materials. What it does with them, in any particular place, remains the greatest open question in science. The universe has a built-in speed limit that applies to information, not just light. While the speed of light in a vacuum is the ultimate speed limit for matter and energy, it is more precisely a limit on the speed at which information, any causally meaningful signal, can propagate. This means not just light, but gravity waves, force carrier particles, and any other physical process cannot transmit information faster than light. The consequence is that the universe is causally structured. Regions of space that are far enough apart can have absolutely no causal connection to each other. The observable universe is bounded precisely by the distance over which light has had time to carry causal influence since the Big Bang. What lies beyond that boundary is not just unknown but currently, and perhaps permanently, causally disconnected from us. The universe is not just large, it is divided into regions that can never know of each other's existence. The first galaxies formed within a few 100 million years of the Big Bang. Among the most dramatic revelations of the James Webb Space Telescope has been the discovery of galaxies at extreme redshifts corresponding to distances so vast that the light we observe was emitted when the universe was only 300 to 400 million years old. Some of these galaxies are surprisingly bright and well-structured, suggesting that galaxies can assemble more quickly than many theoretical models had predicted. Observations of JADES GS Z14-0, currently among the most distant confirmed galaxies, reveal a system that existed when the universe was only about 290 million years old, and yet it appears to contain hundreds of millions of solar masses of stars. The early universe was not a quiet, gradual place. In some regions, it was furiously productive, building structures of extraordinary scale in cosmological terms almost immediately after the lights came on. Quasars are powered by the most efficient energy conversion process known. When matter falls into a supermassive black hole, it can release up to 40% of its rest mass energy as radiation through the process of accretion. For comparison, nuclear fusion, the process that powers stars, converts only about 0.7% of rest mass energy into radiation. This extraordinary efficiency is what makes quasars so luminous. They are not burning fuel in the conventional sense. They are harvesting the gravitational potential energy of infalling matter with a conversion efficiency unmatched by any other process in the universe. A quasar with a black hole accreting at a significant fraction of the Eddington luminosity can outshine its entire host galaxy, 100 billion stars, by a factor of hundreds or thousands. The universe's brightest objects are paradoxically powered by the darkest structures within it. Some stars are so large that if placed at the center of the solar system, they would extend past Jupiter. Hypergiant stars represent the extreme upper end of stellar mass and size. Uy-Scuti, one of the largest known stars by radius, has a radius approximately 1,700 times that of the Sun. If Uy-Scuti were placed at the center of the solar system, its surface would extend past Jupiter's orbit. These enormous stars are extraordinarily rare and short-lived. They burn through their fuel in only a few million years, compared to the Sun's 10 billion-year lifespan. Their surfaces are relatively cool despite their enormous energy output, making them appear red. Their outer layers are loosely bound and constantly shedding material in powerful stellar winds. These stars are approaching the upper limit of stellar mass and stability. Above a certain mass, radiation pressure becomes so intense that the star cannot hold itself together at all. The Sun's magnetic field reverses about every 11 years. The Sun's activity follows an approximately 11-year cycle driven by its differential rotation and internal magnetic dynamics. The Sun's equatorial regions rotate faster than its poles, which stretches and tangles the magnetic field lines over time. Magnetic activity builds. The number of sunspots increases, solar flares become more frequent, and coronal mass ejections become more energetic. At solar maximum, the Sun's global magnetic field reverses. North and south magnetic poles swap. Then activity declines towards solar minimum, and the cycle begins again. This cycle influences Earth in measurable ways. The frequency and intensity of auroras increases around solar maximum, and the stream of charged particles from the Sun, the solar wind, varies in strength. The Sun is not a steady, constant star. It breathes in cycles, shifting its magnetic personality every decade with consequences that ripple through the entire solar system. A single galaxy can contain more stars than there have been seconds since the Big Bang. The most massive galaxies known, giant elliptical galaxies at the centers of rich galaxy clusters, contain up to 100 trillion stars. By comparison, the number of seconds that have elapsed since the Big Bang is approximately 4.3 times 10 to the power of 17, or roughly 430 quadrillion seconds. A galaxy of 100 trillion stars contains about one star for every 4 to 5 seconds since the Big Bang. If you counted one star per second from the Big Bang, you still would not have finished counting the stars in such a galaxy. These behemoth galaxies, called giant ellipticals or CD galaxies, formed over billions of years through repeated mergers of smaller galaxies and are now settled. Ancient systems dominated by old red stars, surrounded by vast clouds of hot X-ray emitting gas. They are the largest gravitationally bound stellar systems known in the universe. The cosmic microwave background reveals the universe's composition with extraordinary precision. By analyzing the precise temperature fluctuations in the CMB across the entire sky, cosmologists can determine the composition of the universe, the proportions of ordinary matter, and dark energy, with percent-level accuracy. The pattern of fluctuations at different angular scales encodes information about how sound waves propagated through the early universe's plasma, which in turn depends sensitively on the amounts of different components. Current measurements indicate that ordinary baryonic matter makes up about 4.9% of the universe's total energy density, dark matter about 26.8%, and dark energy about 68.3%. These are not rough estimates. They are measurements precise to within fractions of a percent. In a universe where most of the content is invisible and unknown, we nonetheless know its proportions to remarkable accuracy from a map of 380,000-year-old light. The most distant known objects in the universe are receding from us faster than the speed of light. This statement sounds like a violation of special relativity, but it is not. Special relativity prohibits matter and signals from moving through space faster than light. It says nothing about how fast space itself can expand. In general relativity, the expansion of space is not subject to the same speed limit. Galaxies beyond the Hubble radius, currently about 14 billion light-years away, are being carried away from us by the expansion of space at rates exceeding the speed of light. Light they emit today will never reach us. Galaxies we can currently observe were within our Hubble radius when their light was emitted, even if they have since been carried beyond it. The recession speed that exceeds the speed of light is not the motion of any object through space, but the stretching of the space between them and us. The largest explosion in the universe since the Big Bang may have been a black hole eruption in a distant galaxy cluster. In 2020, astronomers reported evidence of an extraordinarily powerful eruption from a supermassive black hole in the galaxy cluster Ophiuchus, approximately 390 million light-years away. The explosion created a cavity in the hot gas of the cluster measuring about 1.5 million light-years across, roughly 15 times the diameter of the Milky Way. The energy released in the explosion was estimated at about 10 to the power of 61 ergs, 5 times greater than the previous record holder. Events like this, driven by the jets of supermassive black holes, may play a crucial role in regulating the temperature and density of the intracluster medium and preventing the catastrophic cooling and collapse of gas into new stars. Black holes do not simply accumulate matter. They return it to the universe in the form of energy and jets that reshape the large-scale structure around them. The Sun is not a typical star, but it is a very common type. When astronomers catalog all the stars in the Milky Way, the Sun falls in the middle of the distribution in some ways. Not particularly large or small, not particularly hot or cool, but in absolute terms, it is more luminous and massive than the majority of the galaxy's stars. The most common stars in the universe are red dwarfs, small, dim, cool stars with masses ranging from about 8% to 60% of the Sun's mass. Red dwarfs account for approximately 70 to 75% of all stars in the Milky Way. They are extremely long-lived. Some will burn for trillions of years, and they are the most common hosts of exoplanets. The Sun is more unusual for being as bright and massive as it is than for any other feature. We live around an above-average star by most metrics, a yellow dwarf in a galaxy dominated by quieter, dimmer, longer-lived suns. The universe becomes a more hospitable place for life over time. The earliest epochs of the universe were inhospitable. There were no heavy elements for forming rocky planets, radiation levels were high, and galaxy environments were more violent. Over cosmic time, as successive generations of stars enriched the universe with heavier elements, as galaxy environments calmed and star formation rates stabilized, the conditions for life have arguably improved. Many astrobiologists consider the current era of the universe to be among the most favorable for the emergence of life. There are enough heavy elements, enough stable planetary systems, and enough time for evolution to operate. The far future of the universe will again become less hospitable. As star formation declines, new planetary systems will become rarer. We may live in one of the most fortunate epochs in cosmic history, a time of maximum cosmic hospitality. The universe can generate structures through the cooperative action of quantum mechanics and gravity. The interplay between quantum mechanics and gravity is responsible for an extraordinary range of structures in the universe. Quantum mechanics governs the behavior of atoms, molecules, and chemical bonds that make up solid matter. Gravity operates on the large-scale distribution of that matter. Together, they produce not just stars and planets, but the specific sizes, densities, and structures of these objects. The Chandrasekhar limit, the maximum mass of a white dwarf, about 1.4 solar masses, is a quantum mechanical result. The masses of neutron stars, the existence of black holes, the sizes of stellar cores, all are set by the interplay of these two forces. The universe at every scale reflects the collaboration of the very small and the very large, the quantum and the gravitational, working together to produce the structures we observe. Every proton in the universe may be stable for at least 1 billion trillion years. Protons, the positively charged particles at the heart of every atomic nucleus, appear to be extraordinarily stable. In the Standard Model, a proton should not decay at all on any accessible timescale. Some extensions of the Standard Model predict proton decay over timescales of at least 10 to the power of 34 years, a number vastly larger than the current age of the universe. Experiments in giant underground tanks of ultrapure water have looked for the signature of rare proton decays and found none, placing progressively tighter lower bounds on the proton's lifetime. Whether protons are truly eternal or whether they decay on unimaginably long timescales shapes the ultimate fate of matter in the universe. If protons decay, then in the extremely distant future, even white dwarfs and neutron stars, the last luminous material objects, will slowly dissolve into lighter particles, and eventually all matter will be gone. The universe contains objects that have been isolated for billions of years. In the cores of the very richest galaxy clusters, certain old stars appear to have been isolated in the intracluster medium, the space between galaxies, for perhaps 10 billion years or more. Called intracluster stars or intergalactic stars, they were stripped from their host galaxies by tidal forces during galaxy mergers and have been drifting through the hot, low-density gas of the cluster ever since. These stars orbit the center of mass of the cluster as a whole rather than any individual galaxy, tracing paths that can take billions of years to complete. They are lonely travelers in the most extreme sense, separated from any galaxy for longer than the solar system has existed, lit by no local concentration of stars, passing through the dark, hot void between galaxies in slow, solitary arcs. The universe has a natural tendency to form complexity from simplicity. From a uniform, nearly featureless hot plasma, the universe has produced, over 13.8 billion years, galaxies, stars, planets, oceans, molecules, cells, nervous systems, and minds. This progression from simple to complex appears to be a natural consequence of the universe's initial conditions and physical laws rather than a fluke or an improbable accident. Gravity amplifies small differences into large structures. Nuclear physics creates a wide range of elements with different chemical properties. Electromagnetism enables the complex chemistry of molecules and materials. The weak force enables nuclear transformations that drive stellar evolution. These four forces, working together over sufficient time and space, tend to produce increasing complexity. Whether this tendency toward complexity is a fundamental principle of physics or an emergent property of the specific constants and laws of our universe remains an open and fascinating question. Some astronomical observations take decades or centuries to complete. The orbit of a distant comet around the Sun may take tens of thousands of years. The precession of Mercury's orbit, the tiny advance that confirmed Einstein's general relativity, required centuries of accurate observations to detect. The motion of nearby stars across the sky, called proper motion, is measurable only over years or decades. Some binary star systems have orbital periods of thousands of years. The gradual darkening of a star as its companion transits in front of it, the transit method used to find exoplanets, requires precise and repeated measurements over years. Astronomy is a patient science because the universe operates on timescales that range from the microsecond flashes of magnetar bursts to the billion-year evolution of galaxies. To study the universe properly, you must be willing to wait, or to look at the accumulated observations of generations of astronomers who waited before you. The universe emits radiation in every direction from the remnants of ancient stars, old white dwarfs, neutron stars, and the hot gas in galaxy clusters all contribute to the diffuse background radiation of the universe at X-ray and extreme ultraviolet wavelengths. The cosmic X-ray background, first detected in the 1960s, was initially mysterious, a faint, uniform glow of X-rays from all directions that seemed to have no obvious source. It is now understood to be primarily the summed emission from millions of faint, unresolved quasars and active galactic nuclei, distributed across the entire sky and across cosmic time. This background is not a single event or a single source. It is the accumulated glow of black holes feeding across billions of years, integrated into a diffuse haze of ancient energetic light. The sky, examined at X-ray wavelengths, is alive with the residue of galactic violence stretching back to the universe's most active era. There may be habitable planets orbiting stars that have already died. Red dwarf stars, the most common type in the galaxy, have lifespans of trillions of years. Some of the first red dwarfs to form in the universe are still burning today, their slow nuclear fires barely dimmed. But around those earliest stars, planets may have formed and conditions may have arisen for life. Life that has potentially had not millions but billions of years to evolve, adapt, and develop. If life around these long-lived stars develops intelligence, it has had far more time to do so than life on Earth has. On the other hand, the young universe lacked heavy elements like carbon, oxygen, and phosphorus, the building blocks of biochemistry as we know it. The first habitable planets may have formed only after several generations of stars had enriched the surrounding gas with these elements. But once the conditions were met, red dwarf planets had all the time in the universe. The universe is older than many of its constituent objects. This sounds paradoxical until you remember that the universe did not form everything at once. The oldest stars formed within the first few 100 million years. But some stars, including red dwarf stars with masses just barely above the limit for nuclear fusion, will outlive the universe as we currently understand it. They will still be burning long after the observable universe has changed almost beyond recognition. Planets form continuously as long as there are stars. Molecules form continuously as long as there are atoms and energy. The universe as a whole is aging, but it is constantly making new things within itself. The universe is old, but within it are objects in every stage of their lives. Newborn protostars, middle-aged stars like the Sun, dying red giants, ancient white dwarfs, and in the spaces between them, clouds of gas and dust waiting quietly for the gravity that will start the next cycle. The universe's energy budget is dominated by its own expansion. Dark energy, which drives the accelerating expansion of the universe, makes up roughly 68% of the universe's total energy density. This is more than the combined contribution of all matter, dark and ordinary combined. In a sense, the dominant force shaping the universe's evolution and ultimate fate is not the gravity of its matter content, but the expansive pressure of its own energy budget. This is not well understood at a fundamental level. Dark energy may be a cosmological constant, a fixed energy density of empty space, or it may be a dynamic field that changes over time. If it is truly constant, the expansion will continue to accelerate forever. If it is dynamic and can change, a wide range of possible futures opens up. The universe's most important physical component is also its least understood. The farthest humans have ever sent an object is about 24 billion kilometers. Voyager 1, launched in 1977, is currently the most distant human-made object. As of 2025, It is approximately 24 billion kilometers from the Sun, well into interstellar space beyond the heliopause. At its current speed of about 17 kilometers per second, it would take about 73,000 years to reach the nearest star system, Proxima Centauri, if it were heading in that direction, which it is not. Voyager 1 carries a golden record with sounds and images of Earth, a message from humanity intended for any intelligent beings that might someday find it. The record is not expected to encounter another star system for tens of thousands of years, if ever. The most distant outpost of human civilization is a golden disk drifting alone through the darkness between stars, carrying a greeting to a universe that may or may not have anyone to receive it. Above all, the universe is extraordinarily old and patient. It is never in a hurry. A star forms over millions of years. A galaxy evolves across billions. The cosmic web grew from tiny quantum fluctuations over the entire lifetime of the universe. The first stars burned for only a few million years, and yet even that brief cosmic flicker produced the heavy elements that would one day make life possible. Every process in the universe unfolds according to its own timescale, from the microsecond oscillations of atomic clocks to the trillion-year cooling of white dwarfs, from the nanosecond flash of a particle collision to the billion-year orbital dance of binary stars. Against this backdrop of immense and patient time, a human life, curious, warm, and briefly conscious, is something truly extraordinary. And so, as we return from the farthest edges of what we can see, beyond colliding galaxies and ancient light, beyond the first stars and the deepest voids, beyond black holes that bend time and the quantum threads that connect the smallest things, we find ourselves once again at rest, here in this quiet little corner of an unimaginably vast universe. The universe has been here for 13.8 billion years. It will remain for trillions more. And within that immense and patient span of time, you are here for this brief and irreplaceable moment, breathing, thinking, slowly drifting towards sleep on a world formed from ancient stardust, orbiting a star that is itself just one note in a galaxy of 400 billion suns, a galaxy that is only one among 2 trillion others in a cosmos that, even tonight, remains quietly in the process of becoming. Let your thoughts loosen now, like starlight scattering into the darkness. Let your breathing slow, gentle, and steady, like the gradual expansion of space itself. There is nowhere you need to go and nothing you need to do. The universe will continue its work without you for a little while. It has been doing so for billions of years, and it knows exactly what it is doing. The questions will still be here when you wake. The stars will continue to turn. The light will continue to travel. And somewhere 1,300 light years away, new suns are still being born, silently, in the dark. If these peaceful journeys have helped you find rest, consider subscribing to Somniora Mind. You are exactly the kind of person this channel was created for. And if you are still awake, another chapter awaits you here, patient as the universe itself, whenever you are ready. But for now, close your eyes. Let your final thought fade like the light of a distant star, continuing its journey long after its source has gone dark. Sleep well, and let curiosity guide your dreams. Good night.